Okie dokie artichoke. All right, we are in our last, well, I guess our last topic, I would say, in Unit 7. So techniques of integration. Today we're kind of looking at something a little bit more unique. Okay, it's not so much in the technique that we're looking at, but the type of integral that we're looking at. So it's kind of getting to this abstract part of math here. We have to kind of think a little bit more about what we're dealing with, but I think it's a fun problem. So let's, here's a warm up actually on what we've been doing. Take 2 seconds and see if you can recognize the type of integral that we have for this one. Maybe try to solve it. It's one that's similar to one from your quiz, but I'll let you look at that, and then we'll come back to it if we have time. But here is the lesson. Today's lesson is called Improper Integrals. Now, every integral that we've looked at in the past has been, well, proper because we've had we've had definite bounds. So we've had like between A and B, the area has been absolute. It has been an actual area that we can compute. It's been discrete is another word of saying that. We started at A and we ended at B. But look at what's going on here with improper integrals. Okay, look at these intervals. It's negative infinity to B, or A to infinity, or negative infinity to positive infinity. So as you can probably see, an improper integral is an infinite area, infinite bounds. So how can we possibly find the area of an infinite amount of space? Hopefully you can kind of see an example as we go on here. Well, let's look at this example, for instance. How can an infinite region have a finite area? Well, make it finite, and then take the limit. So that's the strategy here. And let's see exactly how that works. So we got the example 0 to infinity of e to the negative x. So I encourage you to maybe graph this on your calculator or on Desmos. We're graphing, we'll say y over e to the positive x, which is e to the negative x. And if you were to graph this bad boy, and I'm just going to draw a very rough sketch, it looks something like this. Okay, and it's wanting us to take the area from 0 all the way to infinity. So all of this area here. Okay. Well, you're probably kind of thinking back to some old lessons and thinking about, okay, well, that kind of makes sense because if you were to take the limit to infinity of the function itself, the value it's approaching is 0. So eventually this area is going to be capped off when we reach infinity. So, I mean, even though we're talking about an infinite space here, it does eventually reach a closed interval or a closed area, if that makes sense. So okay. So we can take the area of infinite amount of space, and it's when it call converges. When the function converges like this, it's an opportunity for us to take the area underneath the curve. So it says to make it finite by changing the bounds to a finite number. So instead of saying 0 to infinity, we're going to call that 0 to r, e to the negative x dx. Okay? So we're going to make that r. And how we are able to compute infinity in this class is by taking the limit. So I'm going to say the limit is what I'm going to do here of r as it approaches infinity. So this is the same thing as writing it as above, but now I can compute a finite amount. Okay. So let's go through it. So go ahead and integrate. Okay, go ahead and integrate from 0 to r, and then we'll take the limits. So keep that limit on the outside. Integration of e to the negative x is negative e to the negative x. It's just doing a little u sub there. And evaluating from 0 to r. Okay. So you do the integral, and at the very end, you're going to take the limit. So let's just keep going. So that's the limit. R approaches infinity. It's going to be negative, so that I'm going to plug r in for x, minus negative, which I guess will make it plus, e to the negative 0. So, I mean, we're going to take the limits of each of these pieces, and you can distribute the limit if you really want to, and we can write it out so you can clearly see what we're doing. So negative e to the negative r plus e to the negative 0. Okay. All right, so go ahead and just look at the right side first. This is e to the negative 0. It's just a number. There's no r involved in there, so we're just going to figure out what the heck this is. E to the 0 or anything to the 0 is always 1, so that's just 1. And on this side here, okay, if you were to think about this, negative e to the negative r is like saying negative 1 over e to the positive r. And if you were to graph this function, you can look at the graph if you want, but the denominator is getting infinitely bigger. Okay, so this fraction is getting closer and closer to 0 as we approach infinity. So 0 plus 1 is 1. Okay. So going back up to the picture here, that area as we go from 0 all the way to infinity, even though it's an infinite area, it does eventually cap off, and it does compute to 1, because that space to infinity is getting so small that it's pretty much microscopic, if you want to think of it that way. All right, another little vocab word I'm going to use here, and we'll talk about this as we go through the lesson, is that if we are able to compute an infinite area, we say that the area converges. Okay, and I'm sure you've heard that word before. It converges, that's an R. Converges because it's approaching an area. So that's what converges means. Okay. That's kind of the idea of what we're doing today, and all our lessons, all our examples kind of reflect that. Okay. All right, so this just summarizes what we talked about. So this is kind of our note slide here. So to determine the area of an infinite region, number one is you're going to use a fixed value r to replace the infinite bound. So we did that. And then number two is we're going to take the integral of the function. Okay. So A and B are showing you examples of what we just did. Okay, so if it's a to infinity, we're going to let the infinite bound r be on top. And if it's negative infinity to b, we're going to let the r value be on bottom. Okay. And like I said, if the limit exists, if we go through it and we actually are able to compute the limit, then we say that this improper integral converges. And if it does not exist, and we'll see plenty of those examples today, then we'll say that it diverges. Okay. So we looked at A, and which is a similar thing as doing to B. We haven't done an example of, well, C, yeah, I mean, it's just saying the same. But it's mostly giving you an example of how to deal with infinite bounds on both sides. Like you can't really say like negative r to r. Like you gotta split it up. Okay, we're gonna see an example of this later. We gotta split it up at some numerical value a, and then compute two separate integrals. Okay, but regardless, once you split it up, you just take the limit as r approaches positive or negative infinity, and you got your answer. Okay, so let's look at another example. It says show that converges. Well, how we show that it converges is we just show that we have an area, we have an actual value here. Okay, so the process today is super straightforward. Okay, so we're going to show it converges, and if you were to graph this function, I encourage you to do it so you can visualize it. It looks something like this. Okay, and it's wanting us to figure out the area from say 2 to infinity. So this little area right here, and you can probably visualize that it is, you know, the function itself is approaching 0, so the area looks like it's capping off, so we should be good. All right, let's start with the setup. So we're going to limit as r approaches positive infinity, and we're going to replace that infinite bound with an r. And then the rest is just us integrating it. So I'm going to go ahead and write that as x to the negative second, so we're going to be in the right form to integrate. X to the negative second. Okay. No, yeah, let's integrate it. So if I were to integrate it, okay, plus 1 and divide, that would be -1 or -1x to the negative first, or I'll just go ahead and say negative 1 over x evaluated from 2 to r. We're going to plug r in, and we're going to plug 2 in. So we have negative 1 over r, subtract negative, which I guess will make it plus, 1 over 2. Okay. And then we're going to take the limit of each of those quantities separately, and if you want to rewrite it as two separate limits, I think sometimes that's helpful to visualize it. So I got that, and that. Okay. All right, so if you were to take the limits of each of these, so I got the limit of the right side is just 1/2 because it's just a number. Okay. Now, what about the one with r in it? So negative 1 over r. What happens as we approach infinity? Well, you can graph negative 1 over r if you want. It's just the 1 over r flipped, so it looks like this. But as my function is going to infinity, it's approaching 0. So the denominator is getting infinitely bigger, so this limit is 0. So my final answer is 1/2. And therefore, since we do have an actual numerical answer, we can say that this bad boy converges. So we proved it. Okay. All right. So pretty similar to the first example. Let's look at something different. Okay. Determine if it converges or diverges. So it converges if we have a numerical answer, and it diverges if at any point we've come across us saying does not exist. Okay. Now, this is a very interesting problem, 1 over x, and one that's going to require some explanations in further lessons as well. But if you look at 1 over x, it's very similar to what the area looked like in our last example. So 1 over x looks like this. Okay? And we're wanting to find the area from negative infinity all the way up to negative 1. So it looks like this area right here. Now, I usually in class I'd ask the question, okay, so what do you think? Do you think we're going to have an area that converges or diverges? We can have a little discussion there. Well, let's just see what happens when we do this. Okay. So, not a terrible setup, I don't think. We're going to do the limit as r approaches infinity. Okay. And instead of negative infinity, instead of positive infinity, we're going to say negative infinity. I apologize, because it is a negative infinity. And so instead of saying negative infinity, we're going to say negative r to negative 1 of 1 over x dx. Okay? So again, we set it up by doing negative infinity instead of positive infinity because we're going from a different direction in this case. Oh, and I'm so sorry. I don't know why I made that negative r. We're making positive r approaching infinity. I'm sorry. That should be positive r. Okay. Okie doke. So now let's integrate this bad boy. So we got the limit as positive r is approaching negative infinity. And then the integration of 1 over x is the ln absolute value of x. We're evaluating from r to negative 1. Okay? Which we have the limit as r approaches negative infinity. And we're going to plug in negative 1 and subtract, plugging in r. So I'm going to go ahead and split up the limits as we do that. Let's skip that step. So that's the ln absolute value of negative 1. Okay? And then minus the limit as r is approaching negative infinity of the ln of the absolute value of r. Now, let's compute each of these limits. So the first one here, ln of absolute value of negative 1, it does not have the variable r in it, so it's just a number. And the ln of, that's positive 1, would be 0. Okay? And then minus. Now let's think about the ln of r. If you were to, the absolute value of r, actually. If you were to graph the ln of absolute r, and again, I encourage you to try to look at it. This is what ln of r looks like. absolute value looks like this. It just reflects it across the y-axis there. So as we approach negative infinity, okay, as we approach negative infinity, this function is getting bigger and bigger and bigger and bigger. This value, this limit, actually just equals infinity. So we got 0 minus infinity, and if any moment we get an infinite bound or does not exist, we don't have an area here. We don't have a contained area. So, therefore, it would be divergent. Now, that's probably a weird idea to you, right? Because look at the area right here. It looks like as the area is going to infinity, that it's eventually going to cap off, much like the area did for 1 over the 1 over x squared. Okay, so that's a weird idea. Now we're gonna discuss that further a little bit more when we get to our last unit, our series unit, because there's a better explanation then. But the thing is, and if you look at the book for Unit 7, if you look at the book for Unit 7 explanation as to why this is the way it is, why this does not exist, but 1 over x squared does, it states that 1 over x squared, which was this function here, 1 over x squared reaches infinity much quicker than 1 over x. It's so funny, that argument, because like you'll be able to compute the area underneath the curve to infinity for like 1 over x squared, 1 over x cubed, 1 over x to the fourth, because they reach infinity quick enough. But it's funny, it's at 1 over x where it starts to not reach infinity quick enough for us to be able to compute the area underneath the curve. And when I say to infinity, I mean that it's approaching 0 quick enough. So like 1 over like x, 1 over the square root of x, cube root of x, as we start going the other way with the powers, we're not able to compute the area underneath the curve to infinity. And it's just a weird idea because they all look very similar. So just a little something to think about, but we'll come back to that idea later. For right now, we just trust the math. Okay, we just trust the math. We got an infinite bound, so we don't have an actual concrete area, so that would be a divergent area. Okay. All right, now, so we did a few examples of doing infinite bounds, right? So we have like, an upper bound to infinity, a lower bound to infinity. I want to take this second to also talk about another type of improper integral, and it's whenever we have a discontinuity at an endpoint or somewhere in between the integrals. Okay, so let me give you a little example here. We're going to do plenty more after this, but we have a discontinuous integrals at endpoints. So look at this. If you were to graph, for instance, like 1 over the square root of x, I'll just kind of draw a quick little sketch right here. I encourage you again to graph it. But that's what it looks like. And we have a vertical asymptote at 0. So from 0 to 1, we have this area here. But as it goes to the left, as it goes to 0, that's going all the way up to infinity because it's an asymptote. Well, it's going to be the same exact setup as before. Even though it's not an infinite bound, it's undefined technically at that point. It's a simple, quick fix. All you're going to do is the limit as r is approaching. Now, not infinity, but it's approaching 0. Now, which direction is it approaching 0 from? It's coming from the right side. Okay, so it's approaching from the right side. So we say 0 from the right. And then r to 1, x to the negative first. Okay. Now the thing is like, especially if this is going to be a convergent area, which a lot of times it is, if you were to just like go ahead and integrate this just as it is, and then plug 1 in and plug 0 in, it would have worked out fine for you because the integral would allow you to plug 0 into it, but that's not the correct way to set it up. You got to set it up just like this, okay? Take the integral, we can go ahead and do it real quick. It's not a terrible thing to do, so we got the limit, r approaches 0 from the right. If I were to integrate this, that would be 2 x to the positive 1/2, or 2 square root of x evaluated from r to 1. You can do the limit. R approaches 0 from the right. We can plug 1 into that. Subtract, plugging r into that. And since I'm running out of space, and this is not really the problem I was planning on doing, if you were to take the limits of each of these individually, if you're going to separate the limit, that would just end up being 2 minus, and if you plug 0 into the square root of function, whatever, the square root of r, that's just going to be 2 times 0 over 0, which you get 2. Okay? So, I mean, honestly, if you would have not put the limit, you would have got the same thing because it's defined in the integral. But that's just the correct notation, and that's what they are expecting you to do to set it up. So, anyway, just to kind of clarify the points that we just did here, if it's continuous on A to B, but discontinuous at the endpoint B, so here at B we are undefined. So like if I were to draw this on a number line or something, here's A, here's B. We're continuous at A, but as I approach B, we're undefined. Okay. Well, the limit we set up would then be B from the left, because we're approaching B from the left side. And you just saw an example of from A from the right side. That would be A positive here, because again, if I drew my number line, A to B, it's continuous at the endpoint B, but not at A. So the limit would be approaching A from the right side. Okay. And if there was a point somewhere in the middle of the interval, okay, so like it's not continuous at some point C, which is between A and B, we would have to split up the integral. So instead of A to B, we would do A to C and C to B, where this would be approaching C from the from the left side, and this would be approaching C from the right side. So again, we'll see examples of this after this slide. But I'm getting to a point where I'm about to finish the video. Maybe we can do one example, and then we can try the rest together. Okay. So we'll end with this. So if you were to come across this problem before this lesson, you wouldn't even give it a second thought, because you've never had to deal with having undefined points on the interval. So like 0 to 1, you probably just would have done the integration and just be done with it. But if you plug, for instance, 1 into this, that's the square root of 0 in the denominator. So this point does not exist. If you were to graph this value, there would be a vertical asymptote at that point. So I'm not entirely sure what 1 over the square root of 1 minus x squared is. When I graphed it, it made some weird looking shape like this, but like where at 1, it was some vertical asymptote looking thing. Okay. But the point is from 0 to 1 here, the endpoint is undefined. So what happens is if I'm graphing this area, I'm approaching that upper bounds 1. I'm approaching it from the left side. So this is going to be the limit as r is approaching 1 from the left. Okay, 0 to r, and then 1 over the square root of 1 minus x squared dx. Okay, so that's kind of the point here, is to set it up that way. You probably honestly could have integrated this entire thing before this lesson and not even thought about the bounds, because it would have worked. Okay. All right, so let's do this real quick. So the integration, just negative. The integration of 1 over the square root of 1 minus x squared. Think about it. It looks familiar, doesn't it? What does that equal? Sure, your brain is overloaded with integration techniques by now. That's nothing more than sine inverse. So that's sine inverse of x evaluated from 0 to r. So you're going to plug in r and subtract, plug in 0, and then take the limit of each of those. So I'm going to go ahead and split this up as the limit of sine inverse of r minus the limit of r approaches 1 from the left of sine inverse of 0. Okay. So if you want to compute each of these limits, like on the right side here, there's no r in it, so it's just the sine inverse of 0. So you got to think, what do you got to take the sine of to give you 0? That would just be 0. And then the sine inverse of r. Well, r is just a value. It's 1 from the left, so I'll plug 1 into that. And if you were to graph sine inverse, now I know it's been a minute since you graphed it, but I want to show you something real fast. Sine inverse looks like this. So instead, it's like it flips it to 1 and -1 on the x-axis, and pi over 2 and negative pi over 2 on the y-axis. It makes this shape right here. Okay, remember doing something kind of looks like that? That's sine inverse. So I want to know what approaching like 1 from the left. Well, here is 1, and notice we're coming from the left side. So it's still just what the value is, but I just wanted to visualize it and show you exactly what we're talking about. 1 from the left, because we can't come from the right, we do come from the left. Anyway, that value is pi over 2, and this answer is pi over 2. It's convergent area. So, yay. The math behind all this stuff is not terrible. I'm just trying to get to understand the concept and visualize what we're doing, but the math is never terrible. Just set up an integral and then just do the limit. And you notice the integration is not terrible at all. All right, we're going to save this one and the rest of them for together in class. You're welcome to try this one on your own. It's not a terrible one, but it is a little unique, so just think about that one. And then we'll cover the last topic, which is this, together in class. All right? All right, well, good job, guys. Y'all have a great day, and I appreciate everything that y'all do.